Good day, everyone. I'm Michael Pyrcz. I am a professor at the University of Texas at Austin, and this is part of my course on Subsurface Machine Learning. Today, what we'll cover will be Naive Bayes. We'll get into Naive Bayes for the purpose of classification. First of all, to get started, though, we have to recall some fundamental concepts of Bayesian statistics so that we can just build a foundation. Now, we've covered this before. I have lectures on Bayesian statistics in my geostats data analytics course, and even in this class there was a basic overview of probability that I covered. So if you get stuck on some of this stuff, I'm going to go kind of quick for now, but if you get stuck on it, feel free to go back and look at those lectures. Okay, recall Bayesian statistics. So what's going on here? Well, first and foremost, if you take the product rule, which is able to take a joint probability equal to a conditional times a marginal probability, you can recognize very quickly, if I do a very simple reordering, it just becomes the definition of conditional probability. If I take the probability of B and I put it underneath in the denominator here, it becomes the probability of A given B is equal to joint probability B and A divided by probability of B. Now remember, when we talk about conditional probabilities, we go back to our Venn diagram and we say, what is the conditional probability of A given B? Well, B has occurred given B, then we can shrink our universe from omega possibilities to only B. So now shrink your universe to this. So we're shrinking it. All we can think about is B. B happened. Now you can readily see that that conditional probability is simply going to be the joint A and B divided by B. That's the conditional probability of A given B. Okay, so that's great. That means that this product rule can be explained going back to a Venn diagram. It now becomes axiomatic. We perfectly understand. Well, it follows that we can take the reverse, probability of B and A, and the probability of A and B, and we could fill out these product rules for each one of them. Then it follows there's no reason we should suspect that there's asymmetry in this, that we know the probability of B and A is equal to the probability of A and B. So we can take and substitute into this relationship each one of these two components, and that's how we do it. That's how we get to Bayes' theorem. This is Bayes' theorem right here. Now, what's some comments we can make about Bayesian statistics and how we use Bayes' theorem practically speaking? Well, first and foremost, we're going to show that we can have probabilities that incorporate a degree of belief in an event. We update as new information is made available. And we can solve problems that really would be very difficult to solve using the basic frequentist type of approaches. Now, let's just go and recall a couple of concepts about Bayes' theorem. We're able to make a very easy adjustment to that equation. All we did was take the probability of B and put it on the denominator on the right-hand side, and we get the more popular form of Bayes' theorem. Now, what we're able to see is that, first of all, it's pretty powerful. We're able to go from a probability B given A to a probability of A given B. There's many classes of problems for which we would not be readily able to solve one of those conditional probabilities, but we have the other, and so it makes sense. Having that inversion of the conditionals is very, very useful. The other comment I'd make is that each one of those terms have common labels that are used. The probability of A is a prior, probability B is the evidence term, and the probability B given A is the likelihood, and the posterior is the probability of A given B. Now, something very important is that for this to work, the prior should not have any information in it from the likelihood. In other words, if you gather new data, you can't use it to somehow modify the prior. That would be cheating. That's peaking. And that often happens, and that results in a premature narrowing of the uncertainty represented in the posterior. We are fooling ourselves at that point. The evidence term is usually just a standardization. It forces closure on the posteriors such that, in other words, the sum of the probabilities or integration of the probabilities in the continuous case are equal to 1. Now, it makes sense to switch this around, not just use abstract A's and B's, and communicate this in a much more practical manner. And if I did that, I would talk about the probability of a model, that being the prior, The probability of the new data given the model is a likelihood, and the posterior is the probability of the model given the new data. That's an updated distribution we can work with. So I think that's pretty useful to use those terms. That's all I'm going to cover on Bayes. Now, if you do run into some hurdles as we get deeper into this lecture, please go back to the more complete discussions. I even have examples online for being able to work out a variety of problems in using Bayesian approaches. And we even had recent lectures on Bayesian linear regression if you want to see more about machine learning and Bayes. But for now, let's talk about naive Bayes classification of prediction methodology. So remember, if we're talking about prediction, our fundamental prediction problem is that we're given predictor features, x1 through m predictor features, and we want to predict, for the purpose of classification, the probability of a specific category, C category, category K, K through 1 through big K possible categories. So it could be big K is 3, and we have categories 1, 2, and 3. Not a big deal. In our problems, we'll have just 2 categories. We'll keep it very simple. With naive Bayes approach, we're able to utilize the concept of conditional probability. In fact, our prediction model is the conditional probability, the probability of the category given the predictor features. Now, this would be a very difficult inference problem. We would not likely have enough data to be able to solve for it, so we're going to have to make some simplifications in order to get this done. I forgot to finish that slide. That's funny. Okay. Now, let's talk about the naive Bayes method. How do we do it? We'll start with just looking at what Bayesian would look like, the Bayesian approach, for the purpose of predicting that. So we want to predict the probability of a specific category, 1, 2, and 3, whatever the labels are, given what we can observe with the combination of the predictor features. And we're going to have to solve that for all possible categories. So let's pose this as a Bayesian problem, an updating problem. The probability of the category given the predictor feature combination, their actual results, as a function of the probability of the predictor feature combination given the category, that's the likelihood term, the probability of that category without looking at the data, that's the our prior assessment of the probability of the category, and all divided by the evidence term, the probability of that combination of the predictor features. So we can describe it as posterior, likelihood, prior, and evidence terms. Now let's go through and just talk about each one of the terms with regard to this problem. The prior is really cool, actually. It's independent of the predictor features, in other words, the new data observations, and it's simply our pre-assessment before we saw the data of the probability of each one of the categories. Now it should sum to 100%, that makes sense. And we could imagine a variety of different priors we could assign. You could use some type of previous information before you gathered this new data, which told you about some global proportion of something. In our problem we're going to solve, we're going to have low and high production wells. We're doing energy subsurface data analytics and machine learning. So we'll divide up wells into high and low production for our classification problem. And so we could use some type of global proportion before we gathered this new data. Remember, no peaking, can't use the data. Nothing from the likelihood goes to the prior. We could also use a 50-50, 50% probability of low production and 50% probability of high production. That would be a methodology we can employ too. That would be a naive prior. And we'll show when you use the naive prior, in fact, it has no impact. It really becomes a problem just purely based on the data themselves. Now, we also could consider the evidence term. Now, the evidence term, notice that it doesn't consider the actual category assignment. It's only based on the combination of the predictor feature. So its role is really only to standardize the resulting probabilities to ensure that they sum to 1. If we take the posterior probability of each one of the categories given the predictor features, category 1, 2, and 3, those 3 posterior probabilities should sum to 1. So this is a closure constraint. In fact, if you think about it, we could replace this probability right here as the summation of the conditional probabilities multiplied by the marginal probabilities or in other words, just summing over all of the categories, the numerator in this equation. Now, if you go back to a Bayesian approach, what you recognize is the fact that when you do this multiplication, it's actually equal to the joint, including basically the probability of all the predictor features and the category. And when we're summing over all of the categories, it's a marginalization. We're removing the category itself, and we'll get to this without consideration of the category. So that's kind of cool. That's really neat. Now here's where the nightmare begins. The likelihood term. Look at it. This is really, really difficult. It is potentially a very high dimensional joint with a conditional on the category. So in order to calculate this probability, this is really high dimensional. In fact, it's likely we'd never have enough data to be able to calculate it, and it would be very difficult for us to ever work out. So we're just going to say we're not going to do this. We can't do this. So what are we going to do? Well, often when you have problems in life, the best thing to do is take one step back and then try to move forward. Try a different direction. So I'm going to do something right now that might seem like a step back. Let's take the entire numerator. This is weird, right? The likelihood and the prior. And we can put them together. In fact, I just described this, the idea of taking this product and getting the joint with all of them tucked in together. This is now the probability of all the predictor features and the category all at the same time as a joint. Okay, so we tuck that in, that's fine. So we've done that. Now remember when we talked in the more thorough lecture about Bayesian approaches, we talked about this idea of a recursion, a recursive ability to expand the joint. Okay, so how do we do that? So we take the joint, we just tucked in the prior and the likelihood, we got the joint. Now we can show that the probability of all the predictor features and the category is equal to the conditional for the first predictor given the remainder of the predictor features and the category, multiplied by the joint of just everything emitting that first predictor feature. You see that? Okay, now we can expand one more time. We can expand this term. We expanded this, now we expand this. That will be equal to the conditional probability of the second, conditional upon all of the remainder predictor features and the category, multiplied by the joint of the third predictor feature through the category. You see what's happening here? If we take the general and generalize that expansion, it looks like this. The probability conditional of the first predictor feature given the remaining predictor features in the category times the second one, second predictor feature, conditional on or given the remainder of predictor features in the category, boom, 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 all the way down to when we get to the last predictor feature conditional in the category times the probability of the category. Okay, so let's go ahead and we're going to substitute that in. And you might think, that looks worse. How can that be any better? And I'd agree with you. I don't think we can solve that either. But for those of you, I know some people in my class got a little bit worried because remember we tucked the prior in, we hid it away inside of that joint. Well, good news, guess what? In that expansion, the prior's back. Kind of like the cat, it came back the very next day. It's back. So we're okay, we got the prior, but we've got this recursive expansion of this nasty joint conditional probability. So we've gone from here to here, and we still got our prior. This is quite interesting. We could try to simplify it, and spoiler alert, we're going to simplify it. And we're going to simplify it by making an assumption of conditional independence. Now, for those of you out there, there should be some people gasping because you're right. This is going to ignore conditional relationships between all of the predictor features. But we got to do it. We can't solve this problem yet. So what does conditional independence look like? Well, it's not that bad. We're going to assume the predictor features are independent with each other, conditional to the prediction of the response feature. Okay, so what does it look like? We're basically going to say the probability of x1 given all of the other predictor features and the category is only conditional to the category. We remove all of the other predictor features. That's conditional independence. Yeah, it greatly simplifies our inference problem. We can get this, actually no problem at all. And I'll show you, we just nail it, we'll get it. But we're going to omit any interactions between the predictor features with respect to predicting the category. So that is a bit of an assumption. So let's go. So what's it look like now? That nasty joint conditional up at the top here now becomes this sequence of conditionals, very simple conditionals, x1 given the category, x2 given the category, through xm given the category. And then we still have our prior term there. All we have to do now is estimate a set of conditional probabilities, which aren't going to be too hard. We can get that from the data and we can get that done. And we can now calculate our posture. This assumption of conditional independence is why we call this naive Bayes classifier. It's not just Bayes classifier, it's naive because of the assumption of conditional. Okay, my dog is able to open that door. Nope. Okay, so let's go ahead and talk about how we're going to estimate the likelihood terms. Not a big deal. We need to get each one of them. We can estimate the conditional distribution simply by calculating conditional probability density functions. Basically, all we do is take our data, break it up by category in the training data, and get the distributions for each one of the predictor features given that. We could pool the predictor features for over all of the available samples for a single one of the categories, and then we could calculate the associated probability density functions directly. So that can get done. Now, we could further simplify our work by assuming the conditional distributions are some parametric distribution. That's the naive Gaussian Bayes approach. So, yeah, or Gaussian naive Bayes. So what we'll do is, and we'll demonstrate this, we'll assume the conditional distributions are Gaussian. Now we only have to estimate the conditional mean and variance for each one of them. Okay, so let's go ahead and show exactly how to do this by hand. My dog is joining in now. That's Darby, my rescue dog. Okay, let's go ahead and work through an example by hand. So what we'll do is we're going to estimate high and low production. That's our classification. This is our training data. We got porosity, brittleness. Yes, Darby. Brittleness as a measure. My dog wants attention. And we got high production and low production as our classes. Okay, so all we have to do is we just have to pool all of our data, and we're going to pool it by high and low production into separate training and testing data sets. So we'll take the training set and we'll be able to formulate these conditional distributions. Now it's very straightforward if you think about it. All I have to do is for porosity, calculate the mean and standard deviation of porosity for all low production and for all high production examples. And if I assume a Gaussian distribution, those two parameters are it, and I get the distribution for porosity given low and high production. Then I do the same thing for brittleness, my other predictor feature, and now I'll have that. I'll be able to assess. So really what I have now is 4 distributions. The conditional distribution of brittleness given high production, conditional distribution of brittleness given low production, conditional distribution of porosity given high production, and low production, 4 Gaussian distributions. Now what we can do is we can go ahead and assign a prior probability. Our model's ready. We trained the model. If we got the prior probabilities, we're ready to go. So we got the probability of low production, high production, not a naive prior. I put something else in. Now we're ready to make predictions. Now you notice in the equation we're going to need the probability of brittleness of a certain value given high production, given the category that we're assessing at the time. Now if we go back to the probability density function from the Gaussian, we can look up for a single value. In case of brittleness, we can say for brittleness equal to 40%, this is the distribution of high production, given high production, we can get the probability, not a probability, but the density. Now, what's interesting, because of the nuance of PDFs, we expect that the integrals will all be between 0 and 1, and that the integration from negative infinity to infinity to be equal to 1. But that means that individual density measures can in fact exceed 1. But nevertheless, they are a good measure of relative likelihood. So we don't have to worry about exactly the probabilities. We'll just put these density values directly into the equation. In other words, we'll say the probability of brittleness 40% given high production, we'll just put the density value in. And don't worry about it. It'll all work out inside the math, inside the equation, and we'll in fact be fine. Because the closure term is going to take care of the fact that we're going to be working with values that exceed 1, and they're good measures of relative likelihood, so it all works. So let's go ahead and show you some numbers, or show you how this gets done. We're going to estimate the prior probability of production rates of high or low in our problem. And then what we can do is we can go ahead and estimate the posterior probability of production for any combination of porosity and brittleness. Now, in order to get the probability of high production given a specific porosity and brittleness combination, it's going to be proportional to the probability of that specific porosity value given high production, that specific brittleness value given high production, multiplied by the probability of high. Then we do the same thing for low. Probability of low production given that combination of porosity and brittleness is proportional to the probability of that specific value of porosity from the conditional distribution given low production, that specific value of brittleness given low production from the training distribution, the conditional distribution, multiplied by the prior probability of low. Now, once we've done that, I've used proportional because what happens now is we can assess the probability of high given that combination of predictor features as just simply that component that we describe up above divided by the sum of the probability of high and the probability of low, closure. And there we go. We actually end up with the conditional probabilities we need. Using the Gaussian distribution, we got a very simple conditional probability inference problem. We just need 2 parameters. And for many data sets, even if they're not huge, we're usually able to make these calculations and build a reasonable model. Now on GitHub, I have an example of Naive Bayes available for classification, exactly the problem that I've been talking about. And if you'd like to go ahead and try that out, it's available to you on GitHub. It is available in my Python numerical demos. The name is Subsurface Data Analytics, Naive Bayes. I think it's a pretty well-documented workflow for you all to try out and try to get some experience. So that was my lecture on Naive Bayes. I hope that was useful to you. As always, I'm happy to discuss at any time. I'm the Geostats Guy on Twitter, and I have Geostats Guy lectures on YouTube, Geostats Guy on GitHub with all my worked out examples, repository. I even have stuff in Excel and R and Python. And a new package just recently on Subsurface Data Analytics, Geostats Pi. I am happy to discuss anytime, and I sincerely hope that this was helpful to you. All right, take care.